Hello, my name is Dinesh, and today I'm going to be talking about an adaptive correction scheme for offset-free asymptotic performance in deep learning-based economic MPC. This is a joint work together with Professor Ali Mesbah at UC Berkeley and Professor Joel Paulson at The Ohio State University. Economic model predictive control is a popular optimization-based control strategy that repeatedly solves the optimal control problem for a given initial state x naught, and the first sample is of the optimal input sequence is implemented in a receding horizon fashion. For this optimal control problem, we assume that there exists at least one equilibrium point XE such that XE equals f of XE UE, and we assume that the optimal control problem is strictly dissipative. Furthermore, we assume that a constraint qualification and second order sufficient conditions hold for this problem. Then under these conditions, it can be shown that the equilibrium point XCUE is the unique minimizer of the steady state optimization problem. And strict dissipativity implies that the system is optimally operated at steady state. In order to avoid the high memory footprint and high computational burden, the implicitly defined MPC policy can be replaced with a pre-computed explicit MPC policy. However, this approach can quickly become computationally intractable for large systems, and the extension to nonlinear systems with economic objective is not trivial. Recently, there has been an increasing interest to approximate the MPC policy using a suitable function approximator, for example, polynomials, radial basis functions, or deep neural networks. In particular, deep neural networks have recently been shown to exactly represent the explicit MPC law for linear systems and quadratic cost, and it has also been shown to scale to high dimensional systems. The underlying idea of approximate MPC is as follows. The optimal control problem is solved for various state realizations to obtain the MPC policy, which is then approximated using this xi and the corresponding optimal policy as a training data set. This can be seen as a policy approximation using an expert-based supervised learning or imitation learning technique, where the idea is to imitate the behavior of the MPC policy as faithfully as possible. Although approximate MPCs have been shown to give good closed-loop performance in many examples, there may still be approximation errors due to the choice of the hyperparameters that decide the functional form and architecture, and insufficient training data in some regions of the feasible state space, leading to poor generalization. The closed-loop solution obtained using the approximate MPC policy may thus lead to asymptotic performance losses. In order to address this, in this talk, we first present a control-oriented training procedure to generate training data using closed-loop simulations. We then propose a KKT-derived online adaptive correction scheme to account for the asymptotic performance losses. And finally, we present an offline performance verification scheme to provide probabilistic guarantees that the closed-loop system using the approximate policy converges to a stable equilibrium point. The deep neural network parameters are trained by minimizing some loss function, which is commonly the mean squared error, evaluated over a training data set. A natural choice is the feasible region of the MPC control law. However, determination of the feasible state space for nonlinear systems is computationally intractable and can only be done approximately using some outer reachable set approximations. In addition, it is also unlikely that all the states in the feasible state space are equally likely to be observed during closed-loop operation. Therefore, we propose an alternative method based on a control-oriented representation of X defined in terms of the tube of the closed-loop trajectories. Here, we start with some random sample from a set of initial states X naught, and starting from 1 to the number of simulation steps denoted by nsim, we solve the optimization problem and we implement it on a simulator to get the next state. And we continue the optimization in a receding horizon fashion with the simulator as a plan to get the closed loop control trajectories. A key step in the algorithm is the incorporation of an artificial disturbance or noise that is randomly drawn from a set, which accounts for the facts that the approximate policy is only an approximation to the MPC policy, so that the resulting closed loop trajectories will slightly differ, and unexpected disturbances may occur online that cause our system to deviate from the nominal dynamics. The upper bound here represents a tuning parameter that can be interpreted as a measure of confidence in the nominal model predictions. The closed loop system is simulated until either the final time nsem or the equilibrium condition is reached within some tolerance epsilon. And this step is repeated for nmc number of randomly chosen initial state from this initial state set x0. And this gives us a total of nsim times nmc number of data points. Once the training dataset is generated, we can then approximate our MPC policy by minimizing some loss function. However, as mentioned, the approximate policy may still have some performance losses due to the approximation error. A meaningful performance measure for any control policy pi is the cost along the closed loop trajectory given by this expression here, and the asymptotic closed loop performance is evaluated for when time goes to infinity. The asymptotic performance loss stemming from the approximation error can then be stated as the difference between the closed loop performance under the approximate policy and the MPC policy. In order to minimize the asymptotic performance losses due to the approximation error, it may be desirable to adapt the approximate policy online. However, the closed loop performance under the MPC policy is not available online to quantify this performance loss. Due to the strict dissipativity, we know that the asymptotic performance of the closed loop system must satisfy the KKT condition of this steady state optimization problem. For any equilibrium point, this can be stated implicitly using only U as shown here, and the KKT conditions can be expressed as shown here. Now, we make an assumption that the closed loop performance using the approximate policy converges to some equilibrium point xe prime ue prime. We will later justify this assumption using the offline validation scheme, but for now, let's assume that this assumption is valid. Due to the strict dissipativity, we know that the limit point xe prime ue prime obtained using the approximate policy will not be a KKT point if it is not the same as the optimal equilibrium point xe ue. Therefore, the deviation from the KKT conditions indicates asymptotic performance loss stemming from the MPC policy approximation. We can now use this idea and adapt the approximate control law online to ensure that the limit point satisfies the KKT conditions of the steady state optimization problem. And if we can do that, we can ensure that there are no asymptotic performance losses. Therefore, for offset-free asymptotic performance, we need to add an additional modifier term, delta U, and delta U is updated such that the KKT conditions of the steady state optimization problem are satisfied. For this, we need to estimate the steady state gradients online, which can be done using any model-based or model-free method. So we can use the deviation from the KKT conditions as a means to quantify the performance losses and enforce the KKT conditions in order to achieve offset-free asymptotic performance. Since delta U is based on the KKT conditions of the steady state optimization problem, the gain K in the modified control policy must be chosen such that it does not significantly affect the dynamics, but adjusts the asymptotic performance. That is, we need a timescale separation between the dynamics of the controller and the dynamics of the performance correction. The notion of converging to a limit point that we assumed earlier is central here. This, however, is not guaranteed by design. This would be true if we could learn an exact representation of the MPC policy. However, this is not practically possible. Instead of trying to enforce this assumption in our training procedure, we instead look to verify that it holds by developing a stability test. To do this, we use an indicator function phi of x0, which is equal to 0 if the closed loop system converges to x0 and 1 otherwise. Now, the stability test is successful if for all initial conditions x and x0, the maximum of phi of x0 is equal to 0. Since this is a challenging optimization problem, we resort to computing a probabilistic estimate of the worst case performance by associating a probability measure over the sample space x0. Here we generate NV IID samples and define the empirical maximum over these NV samples. It was shown by Tempo and co-workers that for any accuracy epsilon between 0 and 1 and confidence delta between 0 and 1, if the number of samples NV is chosen according to this equation here, then this probabilistic bound is satisfied. This bound can be roughly interpreted as ensuring the set of points greater than the estimated worst case performance has a measure smaller than epsilon, and this is true with probability of at least 1 minus delta. To apply this in practice, we must simulate the closed loop system with the approximate policy under NV randomly selected initial conditions and determine E hat NV. If E hat NV is equal to 0, then all the closed loop trajectories are stable. If any closed loop trajectory is unstable, then E hat NV is equal to 1, and we can certify that the policy does not meet our requirements, and we must repeat the training procedure. With the modified approximate control policy, if we can ensure that E hat NV is equal to 0, then this implies that the approximate control policy converges to the optimal equilibrium point XEUE. Note that the probabilistic verification can also be performed on the approximate policy PyApprox to validate that the approximate policy converges to some equilibrium point XE prime UE prime. We now use the benchmark Williams-Otto reactor to illustrate the proposed method. The economic MPC problem is set up with a prediction horizon of 60 samples and a sampling time of 1 minute. And the training data set was generated using the control-oriented training with NMC equals 20 samples and NSIM equals 50. The epsilon used here was chosen as 10 to the power minus 3. The set of initial states X naught was chosen to be a box set with each state varying between 0 and 0.7. And the artificial noise W here was chosen to be a normal distribution with zero mean and a standard deviation of 0.01. The MPC policy is approximated using a deep neural network with one hidden layer and 5 neurons with rectified linear units as the activation function, and these hyperparameters were chosen using Bayesian optimization. For an accuracy of epsilon equals 0.05 and a confidence delta of 0.05, the closed-loop system was simulated for NV equals 59 initial conditions that were randomly generated to ensure that E hat NV equals to 0, which implies that the approximate control policy converges to the optimal equilibrium XEUE. The process is then simulated with the MPC policy, which is used as the benchmark, and the approximate policy PyApprox, and the modified approximate policy with online KKT-based adaptive correction scheme. The simulation starts with a feed rate of 1.3 kilograms per second, and at around time t is equal to 600, the disturbance changes to 1.4 kilograms per second. So the figure here shows the closed loop performance with the MPC policy shown in these black solid line, and the approximate policy PyApprox is shown in these solid red line. Here, it can be clearly seen that the approximate policy without any online correction leads to a steady state offset compared with the closed loop solution obtained with the MPC policy. The proposed modified approximate policy PyApprox is also shown in the same plot with red dashed line, where it can be seen that the closed loop performance leads to an offset-free asymptotic performance. The closed loop performance for the three policies are shown in this table here, and we also show the loss where we look at the difference between the closed loop performance with the MPC policy and the two approximate policies, and we can clearly see that by using the online adaptive correction scheme, the loss is much lesser. To summarize in this talk, we first showed how we can generate the training data set using a control-oriented training procedure. We then showed how we can achieve offset-free asymptotic performance by using a KKT-derived online adaptive correction scheme to modify the approximate policy. And finally, we also showed an offline performance verification scheme to provide probabilistic guarantees that the approximate policy converges to an equilibrium point. With this, I conclude my talk, and I would like to thank you for your attention.